Alrighty.
We didn't do it totally awesome, sir.
How's everyone still feeling?
Totally awesome, sir.
Alright. So, basically, the EMF is the device that maintains the difference in electron concentration between the two objects. We start off with an object that had a charge of -4 elementary units and another object that had a charge of +4 elementary units. And basically, even though electrons started flowing across and going through a light bulb and going this way, this object right here would maintain a charge of -4, and this object over here would maintain a charge of +4, because as fast as those electrons came over this way, the EMF was putting them back. And we said earlier that the EMF requires work. Well, EMF is really how much work per charge is needed to get that job done. So EMFs are identified by how much work per charge they do in keeping the left terminal negative and the right terminal positive. Since EMFs are measured in terms of work per charge, what's equal to work per charge? Tommy? Voltage, yes? So basically, an EMF could be considered a voltage source. EMFs are measured in volts. Now the name EMF is a little bit misleading. That's why no one uses the complete name anymore. Everyone uses the acronym to try to get away from the complete name. Because the complete name is electromotive force. Electromotive force. And if you see that word force, you think, oh, it must be measured in newtons. But it's not. The electromotive force is what's used to put those electrons back on that negative terminal so that they naturally want to flow through the light bulb going back that way. So here we have a beaker the beaker, there's an acid. Let's say it's filled up to the yellow line with acid. And in the acid, there's two different pieces of metal. A piece of copper and a piece of zinc. Okay? This piece of metal reacts with the acid, produces electrons. This piece of metal reacts with the acid, uses up electrons, leaves behind a positive charge. Ladies and gentlemen, that's like a simple chemical battery. This is the negative terminal. This is the positive terminal. Now we can connect the wire from here through the light bulb to here, and the electrons will flow. But we're usually not going to draw this situation here. So another way to draw the battery, of course, is to draw like this. Here's the battery. One of the batteries has a piece of metal that sticks out. One has the piece of metal flush. This piece of metal over here reacts with the chemical, with the acid, produces a negative charge. This produces a positive charge. So this is the negative terminal, the positive terminal. The side with the little bump, positively charged. The flat side, negatively charged. Connect the wire. But we're not going to want to draw this out all the time either. So a real shortcut way of drawing out this same circuit draw two lines. The short line is the negative terminal. The long line is the positive terminal. This is the negative. This is the positive. And then the light bulb is where the resistance occurs. We could represent that with a zigzag line because that's where it's really hard for the electrons to go through. So this here is the battery. That right there is the wire. This is called the resistance. It could be a light bulb, it could be a little electric motor, it could be a speaker, something that's using the electrical energy. Now, so far, we've been talking about the electron current. Because we know the truth is, it's the electrons that can jump from atom to atom. So we've been talking about inside this wire right here, there are electrons that want to get away from the negative terminal. So they're like, yay, yay, yay. And they go this way, and they go that way, and then they go through the resistance, and then through over here, and then back around like that. But here's the thing. Even though that's what's actually happening, we're not going to be using the electron current. So let's go back to a more simpler diagram. Let's start off with our positive, our negative 4. And let's say this is positive 4. And let's say we connect a wire through a light bulb. Go back over here. So this is a little bit annoying at first, but you get used to it, folks. We know the truth is, if one of these electrons ends up going across over to here, yes, then what would be the charge over here on the left? And what would be the charge over here? Yes? And that's when we have one electron going that way, yes? Which we know that's how things really do happen. Okay? But watch this. Let's just pretend for a moment, shall we? Even though we know the protons are locked up in the nucleus, and the protons cannot jump from atom to atom. Yeah? But just for giggle's sake, let's just pretend that one proton flowed the other way. Yes? Let's say we had a proton flowing that way. Well, if one of the protons went the other way, what would be the charge over here? What would be the charge over here? Same thing we got before. So mathematically speaking, does it really matter if we talk about electrons flowing this way, or if we talk about fictitious protons flowing the other way? It doesn't matter. And guess what everyone uses? Because Benjamin Franklin got it wrong. Negative or positive charge flow?
Positive.
Positive charge flow. Okay? Benjamin Franklin thought it was the positive charges that were flowing. He started doing it this way, and we still do it this way today. This current going this way, ladies and gentlemen, this positive current is called the conventional current. Oh, I ran out of room there. Conventional current is a fictitious. Did I spell that right? Fictitious?
F-I-C-T-I-C. Close enough. It's close enough.
No, it's not close enough. Does anyone know?
F-I-C-T-I-C. I-O-U-S. That's a...
When I say fictitious, I mean it's not real. There is no positive charge flowing in the opposite direction.
It's a T, not a C.
It is a T.
Yeah.
That's what I said first.
Come on, Reed.
What are you
doing?
So that's like, even with batteries, people would be like, oh, watch out, that's the positive end. As if that's more dangerous than the negative end. But people think that the current, the electricity, is going to flow from the positive to the negative. But it really flows from the negative to the positive. All right, sir.
I just wanted to say hi. I'm just in the school,
Oh, well, good to see you. Stop by after school, but I gotta keep teaching right now. Conventional current fictitious pleasure that flows in the opposite direction.
Oh, and then they would. Exactly.
And then they'd be like, wait, what? Couldn't get back in.
Oh, the window.
Yeah, I know.
All right, so if you had a simple circuit here, ladies and gentlemen, you're supposed to know which is the negative terminal and which is the positive terminal of the battery. Cedar, do you remember which is which? The short little guy is the, and the longer one is the? Are you positive?
Exactly.
Good. So we'll answer this question, then we'll take our 2 o'clock stretch. Conventional current flows from A to B or from B to A? Yeah, the conventional current is going to be flowing this way. It's going to flow from B to A. This circuit up top is a mechanical circuit where a person is lifting up bowling balls and putting them on a slide up here. Okay. That's just slightly slanted, yes? And basically, the bowling balls roll down the slightly slanted slide, and then they go down these steps, bam, 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 and then they go down another gently sloped slide. And this person gets a workout by lifting up the bowling balls and putting them up top and keeping the circuit going. So the person's like, yes? And they just keep on putting the balls up here. Now, when they lift that ball up and they put it up here, they're doing work, and now what does the bowling ball have when it's up there? Yeah, the bowling ball has potential energy when it's up here, yes? Okay. And then as it goes down this slide here, it's losing a tiny bit of potential energy, but not much at all, because, it's just a slight slant, okay? But now, boom, 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 it's losing a lot of its potential energy. And in this example, the potential energy would be probably turned into like heat and sound. You'd hear a clanking noise, boom, 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 and probably the temperature of the ball and the temperature of the steps would be going up. Well, you could compare that to an electrical circuit. Now we're thinking of a fictitious positive charge, and when you have a positive charge right here, okay, the battery puts it up here, and when it's next to that positive terminal, it has electrical potential energy. And it basically maintains that same electrical potential energy all the way through here. But then when that positive charge goes through the resistance here, it loses its electrical potential energy, and it might turn into heat, or it might turn into light, or it can be used to turn a motor. But basically, then the positive charge flow comes back. And then what does the battery do? The battery puts the positive and lifts it up, just like the person above, and puts it back on the positive terminal to start the process over again. Now, does the person on the top supply all of the bowling balls? Does he keep taking bowling balls like out of his backpack and putting them on the ramp? No. The bowling balls are already in the circuit. He's just doing the work to raise them up. Yes? Okay. Likewise, is this battery down here? Is this battery providing all of the charge that's flowing through that circuit? No. The battery is just providing the energy to put the positive charge back on the positive terminal so that it'll naturally flow through the circuit. And this leads us to define the two essential things that you need to have a circuit. One, you have to have a complete loop where the object keeps going around the same closed loop. And two, you need an energy source. And when we're studying circuits, the energy source is called the EMF. You need a closed loop pathway for the charge to move through, and you need an EMF, the energy supplier, to keep the charge flowing. Oopsie. All right, so let's just go through these, and then I have one final note I need to talk about. But what is electrical current? Can you define that in your mind without looking back? And if you can't, then go back and look. What is an electrical current? Swati?
Rate of charge flow.
Pardon?
Rate of charge.
It's the rate of charge flow. Okay, and what's the defining formula for current?
I equals Q over T.
Great. And Swati, choose someone to answer the question, what are two different sets of units for current? Choose someone to answer the question, what are two different sets of units for current?
Gary.
Coulombs per second and amperes. Great job. And sometimes it's just called amps for short, for amperes. Okay, second question. Again, see if you can answer in your mind. If not, look back in your notes. What is an EMF? In general, it's a device that
Maintains electron difference between two objects.
true. And also true. True. Okay. Basically, it's the device that will put the charge back on the original terminal to keep the difference in charge concentration the same. In other words, to maintain a constant voltage. When I say EMF, you should think of the voltage source. There are two devices that we'll be studying that work as EMFs. Name one of them, Michael. Magnetic generators. Name the other one, Jacob. Chemical batteries. Finally, what are the two essential things you need to have with an electric circuit? Dorothy, can you name one of them? Has to have a closed loop. Great. So the same charge gets used over and over again. And my man Brett, what's the other requirement?
You need an energy source, in this case an EMF.
You need an energy source or EMF. Okay? So, final note. With those EMFs, okay, which again you can think of as the voltage source, and another name for voltage source is a potential difference. If you have a 1.5 volt battery, that means that this terminal is positive and this terminal is negative. But if you have a 6 volt battery, the concentration of electrons on the negative terminal is going to be 4 times as great. And the concentration, or the lack thereof, of electrons on the positive terminal is going to be 4 times as great. So the higher the voltage, the greater the difference in the charge concentration. When you plug things into your wall outlet, and there's a little space here and a little place here, and then there's a little knob for the ground right there, inside your wall outlet, the voltage difference is 120 volts. That means there's a huge difference in charge concentration, as compared to these. The one terminal is really, really, really negative, and the other terminal is really, 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 really positive. So when you think of EMF or voltage source or potential difference, think of difference in electron concentration. And that's my final word, and I'm sticking with it.
Sprint Sandberg.
No, I have to go to
Yeah.
the chains. I have to go to outside S Hall.
What about driving?
Yeah, that's where
Let's go. That's where.